A year on this planet lasts 10 hours. Not 10 days, 10 hours. By the time you finish your morning coffee, this world has completed an entire orbit around its star. And according to everything we know about planetary science, it should be a dead, airless ball of molten rock. But when NASA pointed the James Webb Space Telescope at it, they found something that shouldn't exist. An atmosphere. Not a thin wisp of vapor, a thick blanket of gas wrapped around a world where the surface temperature melts stone. And here's the part that's keeping astronomers up at night. This planet is 10 billion years old, twice the age of our entire solar system. It's had plenty of time for stellar radiation to strip away any atmosphere it ever had. So how is it still there? The answer involves something scientists are calling a wet lava ball. And if they're right, it changes what we thought we knew about which planets can host the building blocks of life. Let's start with what Webb actually saw. In May 2024, the telescope stared at a star called TOI 561 for 37 hours straight. During that time, a small rocky planet passed behind the star 4 times. Each passage gave scientists a chance to measure the planet's temperature by watching how much the total light from the system dropped. Here's the problem. If TOI 561b were just a bare rock baking in starlight, its dayside should be screaming hot. We're talking 4,900 degrees Fahrenheit, hot enough to vaporize most metals. But the readings came back at 3,200 degrees. Still horrifically hot, still a literal ocean of lava, but nearly 2,000 degrees cooler than physics says it should be. Something was redistributing the heat. Something was carrying energy from the permanent day side to the eternal night side. And there's only one mechanism that can do that efficiently on a rocky world. Wind, an atmosphere thick enough to create powerful global circulation. Picture hurricane-force winds screaming across a sea of glowing magma, pulling heat around the planet like a giant thermal blanket. Without that atmosphere, the night side would be frozen solid, while the day side melted into oblivion. The temperature difference would be catastrophic. But here's where it gets stranger. This planet orbits closer to its star than Mercury orbits our sun. 40 times closer. At that distance, the star doesn't look like a bright dot in the sky. It spans a quarter of the entire horizon. The radiation bombardment is relentless. Over 10 billion years, that should have blasted away any gas the planet ever had. Small planets close to their stars are supposed to be stripped bare. That's the rule. That's what we see in our own solar system. 2 Bill Toy 61b broke the rule. The research team, led by astronomer Johanna Teskey at Carnegie Science, tested every alternative explanation. Maybe the planet has an exotic composition. Maybe it's made of lighter rock with a smaller iron core. That could explain why it appears less dense than expected. But it couldn't explain the temperature readings. A magma ocean alone can circulate some heat, but without an atmosphere, the night side would solidify, blocking the flow. A thin layer of rock vapor might form above the lava, but the cooling effect would be tiny compared to what Webb measured. The only scenario that fits all the data is a thick atmosphere rich in volatile compounds, water vapor, carbon dioxide, maybe carbon monoxide, the kind of molecules that absorb infrared radiation, trap heat, and drive powerful winds. And this is where the wet lava ball idea comes in. Remember when I said the atmosphere shouldn't have survived? Here's the twist. What if it's not surviving? What if it's being constantly replenished? Tim Lichtenberg, a planetary scientist at the University of Groningen, explained it this way. There's an equilibrium between the magma ocean and the atmosphere. Gases bubble up from the molten surface to feed the atmosphere. At the same time, the magma ocean sucks those gases back down into the interior. It's a constant cycle of release and reabsorption. For this to work, TOI 561b would need to be extraordinarily rich in volatile materials, far more than Earth, far more than any rocky planet we've studied up close. In Lichtenberg's words, it's really like a wet lava ball. That single phrase captures something profound. This isn't just a hell world with a surprise atmosphere. It's a world where the boundary between rock and air has become blurred, where the planet's interior and exterior are locked in a continuous chemical dance, where conditions that should destroy an atmosphere are instead feeding it. And that raises a question that matters beyond this one distant world. Every planet in our solar system was once molten. Earth was a magma ocean for millions of years after it formed. The atmosphere you're breathing right now may have bubbled up from that ancient lava, shaped by processes similar to what we're seeing on TOI 561b. If magma oceans can sustain atmospheres for billions of years, then the number of rocky planets capable of hosting complex chemistry just increased dramatically. We've been looking for Earth-like worlds in the habitable zone, but maybe we've been too narrow in our thinking. Maybe planets we dismissed as too hot, too close, too extreme could still have the ingredients for interesting chemistry. Not life as we know it, Nothing could survive on TOI 561b's surface but the building blocks, the molecular complexity, the kind of chemistry that on Earth eventually led to biology. The Webb telescope is now analyzing the full dataset to determine exactly what gases make up this atmosphere. Water vapor seems likely, carbon dioxide is a strong candidate, but the team needs more detailed spectral features to be certain. What's already clear is that our models were incomplete. We thought we understood which planets could hold atmospheres and which couldn't. We thought proximity to a star was a death sentence for any gaseous envelope around a small rocky world. TOI 561b just proved that nature is more creative than our equations predicted. And it did so at the edge of what Webb can detect. This planet is 280 light-years away, a speck of reflected starlight lost in the cosmic darkness. Yet we measured its temperature, identified the presence of an atmosphere, and began theorizing about magma-atmosphere cycling. That's the power of precision observation. That's what happens when you build a telescope capable of seeing the invisible. There's one more detail worth noting. TOI 561b orbits an ancient star in a region of the Milky Way called the thick disk. It formed when the universe was young, when the chemical composition of star-forming clouds was different from today. This planet is a time capsule from an earlier cosmic era. What we're learning about its atmosphere isn't just about one distant world. It's about the diversity of planetary evolution across cosmic history. So here's my question for you. If a lava world can maintain an atmosphere for 10 billion years, what else have we gotten wrong about the limits of planetary environments? I want to hear your theories in the comments. Because if TOI 561b has taught us anything, it's this. The universe doesn't care about our assumptions. It just keeps surprising us.